All right, welcome everybody. Thanks so much for joining us. I'm Kevin Murphy with the Office of Water Programs here at Sac State, and we're happy you are attending our second of two Spring 2025 Water Seminar Series presentations. As most of you know, OWP is a training and research organization with a focus on water quality and water resources. And we annually host two fall presentations and two spring presentations. So following suit, we'll have two more presentations this fall, so stay tuned on that. I also want to point out that all the presentations we host are recorded and can be accessed via the Office of Water Programs website. Okay, so today's presentation will be approximately 30 minutes long, and so we should have plenty of time for questions at the end. And we can go a little beyond 1 p.m. to answer questions if necessary. If we simply don't have time to cover all the questions, we'll forward the questions to today's speaker, Art Umbel, as he has graciously agreed to address them via email if necessary. Please submit questions by emailing them to the email address currently showing on the screen, seminarquestions@owp.csus.edu. You can take a screenshot now or also check the chat line where the email address is provided as well. Now for the important part, I want to welcome Dr. Art Umbel. Art is going to tell us about the future of water. Art is a Senior Vice President Emeritus for Stantec Consulting. He is a global leader in promoting planetary sustainability. Professionally, he has served in numerous leadership roles in the water industry, focusing on sustainable approaches to treating municipal wastewater that incorporate innovation and accelerate the adoption of new technology through applied research and practice. His experience includes leading the global wastewater sector for Stantec, directing Stantec's Institute for Applied Science, Technology, and Policy, teaching at the university level, and managing a publicly owned water and wastewater utility. Though retired, he remains in numerous environmental projects, programs, and forums. Art has a BS in Civil Engineering from Kansas State and a PhD in Environmental Engineering from Notre Dame. And with that, I will hand it off to Art.
Thank you very much, Kevin, and really appreciate the opportunity to be here. Let me get this loaded up here. Yeah, thank you for the opportunity. This is a topic that has been on the forefront of our industry for much of the past decade, and it will be continually a very engaging topic in the decades coming forward. So I'd like to address this issue about the future of our water here in our conversation today. The question that everybody asks is, will it be there for us in the future? And I would like to offer some ideas today that will help us to maybe answer that question. As an outline, I'd like to begin by telling the global story of water today. I want to redefine water stress. This is a question that has been posed over the decades. Many agencies, both at the federal and international level, have tried to define this, and I'd like to offer an alternative definition. Part of that definition has to do with the effects on stress with respect to the global urbanization, the influence of geopolitical concerns that have to do with transboundary water situations. And then, of course, the elephant in the room is climate change, and I consider this as a magnifier of many of the stress elements that we will deal with. But at the end of our conversation, I would like to really open it up to everyone to think about what is it that we must do now to address some of these questions. The global volume of water, which we all are very aware of, takes about 1.4 billion cubic kilometers of volume. And this would cover the continental United States, which includes Alaska, by the way, to a depth of about 89 miles. but only 41,000 cubic kilometers of that water, as we know, is available for human consumption. And this is equivalent to water over the continental area of the US of only 13.2 feet of depth. And this must support 8.6 billion people by 2030 and 9.1 billion by 2050. Studies from the past 15 years have showed that by 2030, the globe's water demand will exceed its supply by more than 40%. And if consumption rates that we have today continue, it's expected that by 2030, 2/3 of the world's population will be experiencing water stress for at least 1 month out of every given year. Even with improvements in productivity of water use, primarily in agriculture, there remains a significant demand gap by 2030, and the rate of water use is accelerating year on year. We actually are on this very trajectory today to meet this by 2030. And as environmental professionals, this is our call to action. But is it simply a question of climate change? Well, we'll take this up during this conversation. Water stress has traditionally been described primarily in terms of supply and demand. And the UN's definition of water stress is when the amount of water available for human consumption, which includes agriculture, industry, energy production, and of course, domestic uses, when that drops below 1,700 cubic meters per capita per year, that is defined as severe water stress. And when we put this into the context of the previous slide, where the global population by 2050 is projected to reach 9.1 billion, the message is not encouraging. So let's think about the definition of water stress. Physical water stress considers the volumes of water present within a particular region and time of year that are available for consumption. And this availability is a direct result of local climatological and ecological conditions. An obvious example here would be the Middle East, Sub-Saharan Africa, and believe it or not, Southern California. But water stress also results from consumption, which is more of an economic condition. Developed economies consume much more water than developing economies. But development is only just one factor. People also experience water stress when the infrastructure needed to deliver the water is inadequate. This can occur even when water availability is plentiful. A good example of this is right here in our own country, Flint, Michigan, Jackson, Mississippi, Newark, New Jersey, to just name several. These are all areas where water has been plentiful, but the infrastructure to deliver that water to the user is inadequate. In recent years, stress has resulted from geopolitical conflicts arising from inequities to the access of water. So water stress is influenced by all these physical and non-physical factors. And I want to take a particular note here to this idea of transboundary factors. And we'll discuss this more briefly later. Limited water availability occurs in hotspots globally. Currently, Central, East, and Southern Asia, the Middle East and North Africa, and Sub-Saharan Africa are the most alarming hotspots that are experiencing water stress. This is not surprising. But what is surprising is that Western North America is now included in this list. Also not surprising is the fact that the hotspots coincide with regions of high population. Based on the UN's quantified definition of water stress that we saw a few slides back, in the recent 3 decades, 185 million people fell below that criteria. And in the 3 decades ahead of us, that number is projected to double. But this may seem, however, like an insignificant amount because, as you can see, it's barely 4% of the total global population. But when you consider all components of this new definition of water stress, the picture then is very different. This here illustrates that water stress affects much of the greater area of the global landmass across the world, and thus a much broader segment of global population. And it's when we account for the temporal aspects of water stress. When we ponder the number of months in any given year that an area experiences stress, we find that in many of these cases, these months coincide with agricultural growing seasons. And so this greatly increases the number of people who experience stress because it now links that element to food security. In recent years, the global water community has recognized the significant influence that sociological factors are having on water stress. This has to do with what we now call water security. And global water security reflects the degree to which each person is guaranteed water at an affordable cost to live a healthy, productive life where communities are protected from floods, droughts, and waterborne diseases. It implies a sustainable access to safe drinking water, sanitation, and hygiene services, as well as water to sustain the ecosystems to supply agriculture, industry like energy, and other economic activities. So water scarcity means it requires the responsible use to preserve its accessibility, making sure that there's enough water for all users, including the environment itself. So water availability for all is not really the core problem. And technically, there is enough water for all of us. But it's the distribution of the population that demands that water that is creating the challenge for our globe. And this is the problem of the explosion of urbanization worldwide in recent decades. This here shows that in 1950, only 8 cities in the world exceeded 5 million people. But by 2000, that number had increased to 34. And the majority of these cities were emerging in the Central, South, and East Asia regions. And by 2015, that number of cities that have more than 5 million people had reached 50. And demographers project that by 2050, urban population will reach 6.7 billion, which is 68% of the total global population that will be living in the urban environment. This dramatically increases the urban water demand, and we will see a between 50 and 80% increase in this demand by 2050. And so when we consider the multiple aspects of water stress, this represents a huge increase in urban populations that will face water stress from what they are experiencing today. As environmental professionals, this is another call to action for us. So what about climate change? In this complex global environment of rapid urbanization and economic development, does climate change really play a role? Though there is plenty of evidence that the changing climate is affecting water availability in many regions and in regions where that population is growing, it is actually much less of a contributor to water stress than what we may have thought. In the world today, there are 526 large cities. This is a definition that the UN uses for a city that's greater than 1 million people. And there are 30 mega cities, which are cities greater than 10 million. 193 of the large city category and 9 of the mega city category are in water-stressed regions. 276 of these large cities, however, can address their water stress and scarcity issues using solutions that we are known to be well proven, such as the water use efficiencies by conservation, curbing their rate of urbanization in terms of urban sprawl, reducing their unaccounted for water losses, and then pricing water at its true value. But 15 of these large cities have no such solution today. And two of the mega cities, namely Delhi, India, and Lahore in Pakistan, also have no such solution. Now, as already mentioned, there are multiple factors making up water stress. And among the most impactful of these factors are the socioeconomic and geopolitical conditions that result when a watershed transits political boundaries, as illustrated here in this graphic. Immediately, you will notice that the water available to the downstream users depends a great deal on that which flows from the upstream basin. And the expectation here is that the upstream users are to manage their consumption in such a way so as to ensure expectations of the users downstream will receive what they need and they depend upon. Obviously, tensions arise when these expectations break down. And more than 300 of these interpolitical boundary agreements currently exist today around the globe that involve transboundary water sharing. Unfortunately, the climate that is changing only exacerbates the problem. And the UN predicts that without any intervention in climate change, water stress, particularly in the arid and semi-arid regions that have transboundary water systems, will result in the displacement, I should say forced displacement, of hundreds of millions of people by 2030. And by the way, we are already seeing this occurring today. So let's consider a transboundary issue right here in our own region. This is the Colorado River Compact that was apportioned the right to 7.5 million acre-feet of water from the Colorado River system for beneficial consumption in perpetuity to both the upper basin and lower basin states. This approach reserved the water for the future development in the upper basin, like in the state I live in, and allowed then for the planning and immediate development in the lower basin to proceed. However, at the time, only 17 years of historical rainfall data were available to make an estimate of just how much water the basin could deliver in any given year. And 3 of those 17 years had much higher rainfall events than were typical of the basin. And so they made a guess. And that guess resulted in an entire basin being overprescribed by 15%, and the water rights for that basin were codified based upon that amount. And this is why we are in the quandary that we are in today between these states. In the US Southwest region, we've learned several key facts about transboundary water use dynamics. The first of this is that stress results mostly from the consumptive demand in both the upper and the lower base states, and much less from how well the upstream basin area manages its water. We've also learned that when the consumption to availability ratio exceeds 1, which has occurred in a number of years, it is indeed the upstream consumption that dominates the stress for both the upstream and lower basin states. The bottom line for the Colorado River Basin, however, is that it's all about consumption. It's not about availability. So what does the water future look like for the US Southwest? This shows the minimum, the probable, and the maximum outlooks for Lake Powell levels of water through Q1 2025, which just ended here March 31st. Lake Powell reached its lowest level in March of 2023, sitting then at only 22% of its full level. Fortunately, however, 2023 turned out to be one of the strongest wet years on record, with the lake rising 70 feet by the end of 2023. But to get back to full pool levels, this will take at least a decade of consecutive wet years, just like we had in 2023. This is highly improbable. And in fact, we've already seen a peak in the mid-2024, where the lake now has been declining since then. And today it sits at about 41% of its full level. So clearly, the Colorado River Compact is not a sustainable situation. The transboundary conflict between the upper and lower basin states is a very real fact. And 2026, when this is being renegotiated, is going to result in winners and losers. The Grand Ethiopian Renaissance Dam, or GERD as it is more colloquially known, is a real-world example of a transboundary water involving an international political boundary. GERD is the largest hydroelectric dam in the world, being 5 times the width of Lake Mead's Hoover Dam and nearly 4 times the width of Lake Powell's Glen Canyon Dam. And this project is igniting tensions between Ethiopia and its key neighbors of Egypt and Sudan over the Nile River's waters. Tensions have been rising between these riparian states since GERD began filling back in 2015. It will reach its full capacity later this spring, in late May. Egypt's opposition to GERD largely rests on the argument that because 97% of its freshwater needs are provided by the Nile River, and Egypt's overall water security is now under a serious existential threat. But Ethiopia and their upstream nations claim that they were left out of the Nile Waters Agreement that gave Egypt and Sudan exclusive rights to most of the River Nile's water when it was drafted way back in 1959. So Ethiopia has thus rejected that agreement and claimed unilaterally that it had sovereignty over its adjacency to the Nile's system water, and it would use that water to support the development of a self-sustaining economy. Ethiopia believes that GERD promises its bright future, because as the world's largest provider of electric power, it will be able to export power throughout all of the Horn of Africa in coming years. And at 6,000 megawatts, this claim is a very realistic claim. But keep in mind, this is one of those areas where global water stress is a hotspot that we mentioned earlier. And the impacts of climate change are already influencing this massive watershed. These are complicated questions. When we consider the water needed for food production, we have 2 fundamental sources: the green water, which is the actual rainfall regime that provides water for crops, and the blue water, which is the renewable water that comes from aquifers and surface waters. Agricultural scientists reference the green and blue waters in the context of their capacity to support crop production and its demand. Today, however, 65% of our global crop production is fed by this green water resource. But climate change is affecting the green water resource because of the shifting patterns in rainfall and the shifting distributions in that rainfall and the increase in atmospheric temperature. This is forcing agriculture at a global scale into more and more dependency on blue water resources. And climate change is essentially cruel to blue water. A 1-degree rise in global temperature results in a 20% decline in renewable blue water resources. So farmers have to make a choice when they want to meet the crop water requirements. They can either employ sustainable or unsustainable irrigation practices. Unsustainable irrigation practices will deplete their groundwater stocks. Sustainable irrigation does not. And so this means that blue water security is now tied directly to food security. Sustainable irrigation means providing crop water requirements without depleting the blue water resources. And it's done so by applying aggressive conservation practices on the green water segment. Unsustainable irrigation is the opposite. And this is the reality that climate change is imposing on agriculture because crop production depends on green water to replenish the blue. Agriculture then is being pressured to meet higher and higher crop production targets to meet the global food demands. But to do this, it also means employing unsustainable irrigation practices. And all this stems from the negative impacts of climate change on green water. Globally today, we are extracting blue water for unsustainable irrigation at volumes 33% greater than what is currently available if we employed sustainable practices. If we could simply shift to all sustainable irrigation, there would be a lot more mouths in this world that we could feed. Here again, as environmental professionals, this is yet another call to action. But this isn't just happening in the subtropical regions across the globe. Right here in the US, the changing climate is indeed already affecting major irrigation areas, particularly in the high plains and in Central California, where both are facing blue water stress several months a year. And these months are coinciding with the crop growing season. Let's look at an example that's occurring right in my backyard in Colorado. This is the South Platte River Basin in northeastern Colorado. It covers about 28,000 square miles, ranges in elevation from 14,200 feet at the top or at its upper end to 2,800 feet at its lower end at the boundary with Nebraska. In this region, there are 834,000 acres of irrigated agriculture. And it lies primarily along the riparian areas of the South Platte River network. Now, 834,000 is a small number compared to the 28,000 square miles. It's only about 5%. Still, it contributes 75% of Colorado's agricultural productivity. This is a very productive agricultural region. The topographic diversity across this South Platte watershed creates changes in climate patterns that require different irrigational methods. In the western part, the upper regions of the basins always use flood irrigation, and that makes up 55% of the total irrigation applied across the entire basin. And it relies entirely on surface water runoff. The lower reaches are dominated then by sprinkler irrigation, which rely completely on groundwater. Currently, the amount of surface water being used for flood irrigation in the upper regions exceeds the volumes that are being provided by the snow melt from the mountains. And this means that the downstream groundwater supplies, which are fed by these surface runoffs from the upper regions, is in depletion, right in the areas where the spray irrigation requires it. So to meet the crop demand, extractions of the groundwater or the blue water sources in the lower regions where the higher productivities exist continue to exceed the replenishment. This is unsustainable, and the irrigation practices that are being used in the lower regions are unsustainable. Climate change, unfortunately, is exacerbating this issue, and here's how. This is some work that was done at the University of Colorado, State University of Colorado in Fort Collins on this river basin to try and understand the influence of climate change on agriculture moving forward with time. These graphs here depict the saturated thickness of the alluvial aquifer and how it changes with time due to the current irrigation practices. The model predicts the changes that occur when climate is altered by just 1 degree Celsius increase in global temperature and a 1.3% reduction in precipitation across this basin between now and the end of the century. During this time, groundwater saturation declines between 80 and 100% due to a 36% reduction in the replenishment from the upstream areas of the watershed. The most severely impacted region here is in the mid-basin area. And this is a critical area because it is the primary source that replenishes the aquifers in the lower region. And that's where the crop productivity is the highest. This groundwater depletion impact affects the crop yield. And the models show a decline of 11% by the end of the century. Now, you may not feel like that's very much, but in the context of global food demand, it's a huge number. Again, the maximum reduction here in yield occurs in the lower elevations, and that's where the highest productivity yields have traditionally been. When you correlate the crop yield to the blue water availability, by decade, this data shows that as the groundwater depletion continues, crop yield continues its decline. All of this means that the future of water with respect to the changing climate from a societal perspective is manifested most profoundly in agricultural production. These trends are real, and we are already observing them in this basin. This is a concern because of the influence that this has on the global food security question. What it means for us is that though water stress is, of course, about water availability, it's so much more about how we use and consume our water and the value that we place on the outcome of that use. So, what can we as environmental professionals do? As environmental engineers, we love to focus on the supply side solutions as listed here, many of them. And this is all about advancing technology to be able to supplement or increase water supply. This is, of course, necessary and it's needed, but it is remarkably expensive. And expense relates to affordability, and affordability affects equitable access. But the real solutions come from reducing our demand. And this is all about behavioral change across an entire society. Is there enough water for our future? I would argue absolutely there is. Will it be there for us? I would argue yes, but only if we shift our focus away from supply side solutions and focus on reducing demand. As environmental professionals, I reiterate, this is our real call to action. So in conclusion, our water's future is fundamentally dependent upon consumptive demand. And our future is about scarcity, but more so, it's about water stress. And stress is all about the rate and the scope of our global urbanization. And climate change is magnifying the impacts of these things. Climate change is already impacting our agricultural production, as we've just seen. And 9.1 billion people in 25 years? Oh my. This is a challenging call to action. But we can future-proof our water by targeting the demand reductions. And we do so by adapting to the climate change via these engineered solutions to manage the supply. And with that, I'd like to stop and open it up for discussion. Thank you for your attention.
All right. Thanks, Art. That was fascinating. I just want to remind viewers that you can, if you go on the chat line, you can see the email address where you can send questions. And we have plenty of time for questions, so please submit your questions. Let's see. So, Art, I will just read the questions as they come in. One of the questions is, can you summarize your ideas for reducing demand?
Sure. Great question. And probably one of the questions I get so often is what is meant by this idea of sustainable irrigation in agriculture to help reduce demand? And it is both technological and it's also sociological. From a technological perspective, what we see primarily with the large factory farms in the US, high plains, are transitioning away from large circle pivot irrigation spray systems to what's known as drip irrigation. And the issue there is, or I should say the solution there involves taking the water and putting it directly onto the root of the plant. If you think about spray irrigation sprays everything, right? It sprays the soil, it sprays the plant leaves, it sprays anything that's in its way. And much of the land is, even though it's cultivated, doesn't have plants growing on it, and it gets watered. And so it wastes significant amounts of water. And so the drip irrigation is a way to much improve the efficiency of the irrigation to more sustainable things. There's a downside, however. As you can imagine, moving to the infrastructure that's required to establish drip irrigation is expensive, at least at the initial levels. And many large factory farms across our high plains and high deserts do not feel it is economically advantageous for them to invest in that kind of infrastructure. It's easier for them and more cost effective in their point of view to just use spray irrigation because of the volumes of the product that they're producing outweigh the initial investment costs. So we have to get over that. But we have shown from research and from farms that have already integrated drip irrigation, sustainable irrigation practices, that they've received anywhere from 30 to 70% reductions in water use. And so that's a really significant thing. The second thing has to do with the employment of IoT. We've seen quite a bit of work in this in the last 10 years where we're using satellites and the use of remote and local sensors with satellite data to be able to help the agriculturalists determine when to irrigate and how much and where. And so this has also resulted in dramatic reductions in actual water use in these unsustainable irrigation practices. Other things that are less common, but also extremely effective are things called localized organic mulching. And this helps to increase the hydration locally of right around the plants that need it. And it also dramatically reduces evapotranspiration. Another thing that has been uh, used in some areas of the United States, but not very much yet, is the use of crop tolerants that are effective and associated with the climate of the local region. So instead of growing almonds, for example, in an arid area, which are highly requirements of water, why not grow products or crops that are more tolerant to more arid conditions, which use less water? And this has a long way to go, I think, culturally for us. This is one of those sociocultural factors that I think we have to shift our thinking on. We also found in a number of projects across, primarily in the large factory farms in the Midwest and the upper regions of the Midwest, where groundwater irrigation is substantial, is the reducing the use of chemicals. And the chemical uses, you may say, well, what's that have to do with water and what's that have to do with irrigation? Well, obviously it has a lot to do with the fact of that it affects the moisture contents of soils in terms of its impact on weeds and so on. Contour farming, which was very common and it's still commonly used in areas of Nebraska and western Kansas and northwest Texas. In these areas where you're using the contour of the land, that was originally set up as a means to control erosion. However, it has been found that there's been a dramatic positive benefit on reducing water usage as well. Tillage farming and fallow farming is another method. These are all things that are being practiced in small scales. We need to practice them at much, much larger scales, particularly at the large commercial farming facilities that are farming, tens of thousands of acres, but still using large circle pivot irrigation, spray irrigation. If you fly over western Kansas, western Nebraska, Oklahoma, you'll still see hundreds of thousands of acres of circle pivot irrigation that is, in my opinion, not a sustainable future.
All right, thank you. Let's see. In California, we have the flood more movement, and flood mar is managed aquifer recharge, so taking flood waters and spreading them out over the farmer's field and filling up the aquifer. Do you have any opinions on that? And is that we are starting to use that in California? There's issues on how to get the water there, of course, but do you have an opinion on that? And is it being used in other in your area as well, and in Nebraska and Iowa and those areas?
Yeah. So flood irrigation is a common practice. I'll speak for the Colorado folks. And it's primarily in those areas in the western regions of the high plains where the topography is steep enough that to just have it running off is not very efficient. And so flood irrigation in those areas can be very efficient because it does put water right at the base of the plant root. However, we do have in Colorado, we have a very low humidity, so the amount of evaporation of flood irrigation is very high. And so we have to balance that as well. And the fact that because of some of the steep terrain, we tend to see more of that surface water escaping the opportunity to be recharged into the aquifers in the lower areas, just simply because it runs off. So what they're having to do is to contour the properties so that they can capture the runoff and keep it from escaping, and then including that into areas where they have recharge basins. As I mentioned earlier, with this area of the South Platte in northeastern Colorado, The upper alluvial areas are very conducive to good infiltration into the aquifers. And that's what the lower basin requires and needs, is that infiltration. So these practices are improving that, but we have a long way to go on that. I'm not a big fan of pure flood irrigation, just because of the evaporation that you see from those. We do lose a lot of water from that perspective. So the flood mar in California, I think, is, yeah, we have to do more of that, and we have to manage that evaporation carefully and make sure that we're not evaporating more than we're actually recharging into the aquifers below. So I think it's a great part of the solution to go to more sustainable agricultural practices, but we still have a lot to learn. I would say one other thing. This is very interesting. You might want to check. There's a group in Peru, actually, that has resurrected practices of the ancient Incas in developing this sort of contouring channelization of runoff from the steeper elevations there in the Andes to be able to provide for infiltration into the basins to support aquifers in the lower regions to promote agricultural productivity. There was a recent article that was published in the Nature Conservancy journal that would describe for the reader all of what's going on in that area. And I think it's very applicable to areas that we have in Colorado and areas that on the western slope of Colorado that can do the same thing. And perhaps in the Sierras in California could apply some of these same kind of things. But it's interesting. Those are thousands of years old, those practices, and they're very, very effective.
All right. Do you have any comments on some of the eye-catching solutions for water shortage? Pushing icebergs to places of need, moving water from the Great Lakes to places of need, that sort of thing.
Um, I'll be very honest and say I am not a fan of any of those things. I think, yeah, technology has always sort of been at the forefront of our psyche in terms of that's how we solve problems in this culture, is we just throw technology at it. And we tend to rely on those technologies to, in this case, on the water space anyway, to just simply say we can find more supply in all these technologies, or we can augment supply, or we can supplement supply. Look at desal and these kinds of things, or moving icebergs. Yeah, we can do that. There was a proposal that went from the state level all the way to the federal level back in the late 2000s, that came out of New Mexico, to get to your point, Kevin, regarding moving water from the Great Lakes down to the Southwest in a large pipeline. This was promoted by then Governor of New Mexico, Governor Richardson. And that went all the way to the Senate floor as a proposal, and no one knew about it, or at least no one was aware of it. And so the word came out that this was going to happen, and all of the states around the Great Lakes, including two of the provinces in Canada, got together. And I was part of the commission that worked on this, what was called the Great Lakes Compact at that time. And in 2003, went all the way up then to the federal government, both in Canada and the US, to say, no way in hell are we ever going to let one drop of water out of Michigan Lake or out of Lake Superior or any of those lakes moved to support development in the Southwest. And so it was killed. And that was in perpetuity. So to my knowledge, that compact will always be in place, provided that is always supported by Congress. So am I a fan? No, I'm not a fan of those kinds of things. I think we have a much brighter future when we consider first reducing our demand through efficiencies, through conservation, through changing our behaviors on how we use water, in putting the correct value of water where it belongs, and then allow technology to provide the margins where those supplements are needed. And but that's just my opinion.
All right. And this may be the last question. Where are we with decreasing the total cost and energy needs of desalinization,
Oh my.
considering that many of the places in need are fairly close to the ocean or
Yeah,
right on
indeed.
the ocean?
Yeah, I'm not a big fan of desal. I know it's a strong contender to be a good supplement for drinking water supply, but it's really currently still being focused on the coastal areas because of the brines that are created. We have no way of disposing of the brines in inland areas, plus the fact that you got to pump all the water that direction, so you're taking more energy to move it. We don't see, well, I should say this. We have seen a reduction in the cost of membrane technology in the last 5 years, particularly. The International Desalinization Association has been working hard with technology providers to really publish more about those improvements in cost in membranes. We've moved away from PVDF membranes now because of the PFAS issues. So we're looking more at ceramics and other kinds of membrane technologies, which are enhancing the water recovery of desal. But again, it's really applying itself only in the coastal regions, and the energy costs, though we have seen come down, we still don't have near the reduction in energy costs for promoting desal than we need. And so my position is, why are we spending all this money on desal technology? Why don't we put that money into water reuse and looking at using much different and more proven membrane technologies on the wastewater side to be able to provide adequate augmentation for water supply. There's a big project going on right now up in the Lancaster area in Apple Valley, up in the high desert in California, that's looking at this very thing. And we're also coupling that with, the reduction in greenhouse gas production, which is a big deal with desal.
All right. Art, thank you very much for answering those questions. On behalf of OWP and all of today's participants, we want to thank you for an excellent presentation on the future of water, a topic that understandably has worldwide interests. Uh, so once again, I want to thank you, and I want to thank all our listeners, and I hope everyone has a nice weekend. Take care.
Thank you.